How does mathematics interpret and model living systems? We generate enormous amounts of data every day. Smartwatches record heartbeats, hospitals store blood test results, and satellites observe Earth's weather. But can simply looking at all these numbers reveal new discoveries? Just as scattering thousands of puzzle pieces does not complete the picture, data only becomes meaningful when rules connect it. The most powerful tool for finding those rules is mathematical modeling. Mathematical modeling is the process of describing complex phenomena with mathematics. In simple terms, it is a blueprint of the real world. Just as architects draw a blueprint before constructing a building, scientists create a mathematical blueprint before studying living systems. For example, they use variables and functions to describe how blood sugar changes after taking a drug, how quickly bacteria multiply, or how the heart pumps blood. So, what makes a good model? The answer is a model that explains reality well and predicts the future. Just as a weather forecast predicts tomorrow's weather, a mathematical model predicts how a biological process will change over time. It is easiest to think of modeling as finding the function that connects the input and the output. Most biological processes change continuously over time. That is why they are often described with differential equations. A differential equation describes how fast something is changing at a given moment. When driving a car, it is not enough to know the current speed. It is also important to know how quickly the car is accelerating or decelerating. Likewise, to predict the future of a biological process, we need to know its rate of change. However, the human body is far more complex than a car. The heart, lungs, blood vessels, nerves, and hormones all affect one another, making the differential equations much more complex. Is there a limit to solving them by hand? That is why computer simulations were developed. Instead of testing a drug on a real person first, scientists test it on a virtual human body inside a computer. It works much like testing a new airplane in a flight simulator before its first flight. Today, researchers can even build virtual hearts to predict surgical outcomes and calculate how drugs will act inside the body. Mathematical modeling also plays a major role in brain research. The brain thinks, stores memories, and controls movement as countless neurons exchange electrical signals. But how are these signals created? In the 1950s, scientists discovered that ions pass through cell membranes because of the voltage difference across the membrane. They then used voltage and ion movement as variables to build differential equations. Remarkably, this mathematical model alone could explain how nerve signals are generated. Mathematics made it possible to explain how the brain works, even though we cannot observe it directly. Mathematics is also essential when studying the entire brain, where countless neurons are connected. What happens if some connections between neurons are lost? How do memory and movement change if certain neurons become less active? These experiments cannot be performed on real people. Instead, a mathematical model in a computer can change the connections or weaken specific functions to observe the effects. Mathematics makes these impossible experiments possible. Mathematics also plays an important role in medical imaging. CT and MRI provide detailed images of the body, but they are very expensive. That is why researchers are also studying electrical impedance tomography, a simpler way to image the inside of the body. This technology uses the fact that different body tissues, such as muscle, fat, and bone, conduct electricity differently. Just as water flows differently through clear water and muddy water, electricity also flows differently through different tissues. When a very weak electric current passes through the body, it measures the electrical conductivity of each tissue. However, the measurements alone cannot directly reveal the body's internal structure. This is where mathematics comes in again. By applying Ohm's law, which describes the relationship between current and voltage, along with its extended differential equations, scattered data can be reconstructed into a single image. It is like putting together thousands of puzzle pieces to complete one picture. Life is incredibly complex, but it follows hidden patterns. Mathematical modeling uncovers these patterns, helping us understand the invisible processes of life and predict what will happen next. As AI-powered healthcare, personalized medicine, and drug development continue to advance, mathematics will play an even greater role. A microscope shows what life looks like, but mathematics reveals how it will change. What tool will future doctors rely on most when treating patients? Perhaps mathematics will become as important as the stethoscope.